thank you, Stefano, and thank you, everybody, for being present, and hello also to the people who are watching the streaming. And yeah, this short presentation is about giving some ideas on how to find outliers in data. When we collect data related to some phenomenon, most of them are, let's say, normal. They don't have any specificity, but sometimes it is important to be able to find data that are not similar to the others you are examining. And yeah, this talk is about how to find this data. I just give you some hints on how to do that. And yeah, this is a short outline, a short introduction of myself and of the laboratory for which I work. And yeah, I will give you an introduction on finding unusual events. And this activity is also called anomaly detection. So this is another name for which these algorithms are named. And some short reminder about the Gaussian distribution that is useful to find these outliers, this data. A proposal of an algorithm, very classical, for doing this activity, this outlier detection. And yeah, some words about how to develop and evaluate an anomaly detection system. And in the end, some differences between supervised learning and anomaly detection. These are similar from some point of view, but they are different from others. And it's interesting to point out which are these similarities and differences. Okay, just 1 minute about the laboratory for which I work. Smart Data Factory is a laboratory of the Faculty of Computer Science of University of Bolzano. We are based here on the 4th floor, so in the corner over there. So if you want to come and meet us, we are there. And our goal, our mission is to do technology transfer, to establish cooperation between industries, between public administration, between third sector actors, with connection between these actors and our faculty, the research that is done in our faculty. So we try to foster collaboration between industry and academia in order to build up innovative projects that increase the innovation potential of the territory. And this is an overview of the competencies and skills of our laboratory and our faculty. We have competence in data management, user experience, recommender and decision support system, computer vision, business process manager, software engineering, cloud and edge computing, numerical methods, and bioengineering technologies. This is just a very fast overview about our competencies, and we try to establish cooperation and joint projects on all these, taking advantage of the expertise in all these fields. In particular, myself, I have worked in the past years on application in the medical domain, and in particular on personalization systems in healthcare using artificial intelligence and machine learning. And okay, you can find my details, and I want to go in. I will go on because we don't have much time. Okay, find unusual events. Okay, let's start to talk about the differences between supervised learning and anomaly detection. That is a kind of unsupervised learning. Okay, when we talk about supervised learning, we are given a data set, a training set, and for each example, x1 to xm, a label y is given. So in this case, we have examples made by two features, x1 and x2, and for each example, a label is given. So one label is the x, and one label is the blue cycle. So the goal of supervised learning is to find a way to classify these examples in order to find a separation between them, so that when you get a new example that is not given a label, you are able to find a label to be given to this example. When we talk about unsupervised learning, we have a training set without labels. So in this case, we don't have a label that defines the type of the object of the examples. So we can do different things. One is to, for example, is doing clustering, which means that we are able to group examples that are similar to each other, like in this case, but in another type of supervised learning is to do anomaly detection. So in this case, we have a set of examples that are distributed on a space, and here we know that these examples are in some way normal. So when we are given a new example x on the bottom right corner, so the goal of the algorithm is to find if it's anomaly or not. So in this case, it's much probable that it's an anomaly because it's in a point of the space that is not where the density of the other example is very low. But for example, if it would be here, then the algorithm would conclude that the example is okay, is normal. So let me try to make an example. Here, the example is about detections of anomaly in engine aircraft. Okay, so imagine that we have two features that are that describe an engine of an aircraft. One is the heat generated while the engine is working, is landing, and the other one is how much this engine vibrates while running. So in this case, we have a training set made of very many engines. Each of them is one of these crosses here, and is described by the quantity of heat that is generated and the quantity of vibration that is generated. This is the description of our training set, and when we are given a new engine, let's call it X-test, for example, it could be here in the middle. So in this case, we could conclude that it's okay, it's an engine without any problem. Or, for example, if it's here, so the heat is very low and also the vibration is very low, this could mean that it's an anomaly. And the algorithm is able to find out that this violet X is an anomaly. And okay, so Our goal is to find out if one example, X test, is an anomalous, given one training set. So what we do is to try to estimate the density of the training set, and this is done by modeling the probability of X being seen in the training set. Once we have modeled this density, then we are able to find that the probability that an example is this blue area is very high, in this green area is lower, and in this violet area is even lower. So for the examples in this area, the probability is very high, and for example here in this area, the probability is low. So once we are giving the X test, this violet cross, we calculate its probability, and if it's lower than a threshold, epsilon, then we raise an alarm. Then we find that it's an anomaly. Or, for example, if it's here in the middle, then we can conclude that this example is okay because its probability is in this area of where all the other examples are concentrated in some way. Okay, so where anomaly detection can be applied. These are some examples of application field. Detection of fraud, manufacturing, monitoring computers in data centers. This is just three examples. In this case, for fraud detection, well, here, for example, we want to monitor the activity of user on a website to find out if it's a fraudulent behavior. So in this case, the features can be how often the users log in to this website, how many web pages are visited, how many transactions are made, how many post users post on the websites, what is the typing speed, and other features that we think could be useful to identify fraudulent behavior. Okay. So once we have a set of users that are modeled by these features, then we can find out that the probability of specific combinations of these features and identify unusual users by checking which have the probability less than the threshold epsilon we have set up. Of course, once we have identified a potentially fraudulent behavior, very often it's needed to perform some additional checks to identify real frauds from false alarms that could be the case happen from time to time. In manufacturing, the features are those of a product that we want to monitor. For example, we have seen the airplane engine, but other examples are printed circuit board, smartphones, and so on. Any type of item. Or we can try to monitor computers in data centers. Then in these cases, the features can be the memory use, the number of disk assets, the load of the CPU, or also some ratio, for example, the ratio between the CPU load and the network traffic. And these are features that could be useful to monitor computers in data center if they have some strange behavior and that if they are anomalous. Okay, so 20 minutes are already gone and I am at the beginning of the presentation, so how much time do I have in total? Because I have to try to...
Not that much, till 8 o'clock normally. Normally we go till 8 o'clock, so...
Okay.
You have time.
I have time, okay. We have seen some examples. So now I want to go into some more detail about how to perform this detection of anomalies. And in order to do that, I need to shortly introduce the Gaussian distribution that I'm sure you already know, but okay. So the assumption that we do is that these features have a normal distribution. So this is an assumption that we do, and it's quite normal that this distribution is the one that the features have. So here we have the typical Gaussian distribution. There are two parameters, the mu and sigma, the variance and the mean, and the probability of x is given by this function, and this function is the typical bell shape of the Gaussian distribution. And of course, there are different types of distribution according to the value of the parameters mu and sigma. So, for example, for this mu equal to 0 and sigma equal to 1. Then this is taller but more short. In this case, the sigma is equal to 0.5. And of course, since the area is always 1, because it's a probability, once the sigma decreases, the high of the bell becomes the bell becomes taller, because of course to keep the area constant. Here other example, mu equal to 0 and sigma equal to 2, and here also another example in which the mean is 3. So these are example that and the variable, the values of the features are distributed according to this distribution. And so what we have to do is to estimate the parameters sigma and mu and sigma from the training set that is given, from the normal examples that we are given. Okay, so here we have an example in which x is just a number, we have just one feature, and imagine that this feature is distributed in some way. So this is the different value of the feature that the feature assume along the axis, and as you see in the middle, the density of the example is much higher, and from this distribution we should be able to fit the value of the parameter mu and sigma in order to find out which is the distribution that better describes the examples we have. And this is done as usual. So the estimation of mu is given by the mean of the value of the single feature that we have, and the value of sigma square is the standard, is the classical formula for the standard deviation from the statistical books that we know. And okay, these two formulas gives the maximum likelihood for the two parameters, and this is known from the probability, from the basic theory of probability. So once we have a new value x, so we are able to, using this distribution that we have find out, we are able to calculate its probability p of x, and also, for example, if the new example is here, then the probability is much lower. So by estimating the parameters of the distribution, then we are able, giving a new example, to use the distribution we had found in order to find out the probability and check if this probability is below the threshold we have set up, and then decide if the example is anomalous or not. Given a training set of examples, here you can see that these examples are made of not just by one feature, but these are vector of features, and each example xi has n features in this case, and can be described by a vector of n components. In the case of the engine or aircraft engines, then we had just two features, and they were vibration and heat. But in general, we have n features. Then the probability of x is given by the product of the probability of all the features given their distribution. So this is the probability of feature S1 according to the Gaussian distribution with parameters mu1 and sigma 1 square. And since we have n features, we suppose that these features are independent of each other, and then we can find out the probability of example x by multiplying the probability of all the features. Just to give you an example, if the probability of here we have just two features that are vibration and heat. So the probability of high temperature, let's say it's 1/10, and the probability of x2 equal high vibration is 1/20. Then the probability that a engine has both high temperature and high vibration is the multiplication of the two probabilities. So in this case, is 1/200. And okay, this is just an example about how to calculate the probability. And to sum up, the algorithm for doing anomaly detections. So the first thing that we have to do is to choose an feature xi that we think are indicative of anomalous examples. And this is a tricky point that has to be, this choice has to be done very carefully because the selection of the right features is fundamental in order to be able to find an algorithm that works effectively. And once we have defined, we have chosen the features, then we fit the parameters of these features. So we calculate M1 mun sigma 1 square sigma n square using calculating the average and the standard deviation of the values that we have for the features. And of course these are the formula. So every mu j is given by this formula, and every sigma square j is given by this formula. And of course, this could also be represented using a vectorized formula in which we calculate the average of a vector. Then, when we have fit the parameters, when we are given a new example, x, we compute the probability of x, and this is done by using the formula we have introduced, and of course here we just explicitate the probability since this is a Gaussian distribution, so this is the formula that has to be used. And then we check if the probabilities is less than the threshold we have set up, then we can decide if the new example x is an anomaly or not. Since you multiply the probability, it's sufficient that one of the features is very, let's say, strange. Example, in this case, we have we have xj, the feature xj's, with probability is very low. Since you multiply, just that feature is very strange, then this makes the whole example anomalous, and because the probability is very low, so this product is also very low. And okay, let's try to see with an example how the algorithm works. And here we have one example in which we have two features. So our training set is made of examples with two features, x1 and x2. And for x1, mu is equal to 5 here, and sigma 1 is equal to 2, so the distribution is rather large, while in the other direction, for x2, then the mu is equal to 3, so it's here, but sigma is lower than before, since you can see that the concentration of the example is restricted in a small area in the center of the figure. So this is the distribution of x1, and this is the distribution of x2. Then, when we try to, this is the shape of the combined distribution, combined probability of x1 and x2, and here you can see that the probability of the top of this bell, 3D bell, is the correspond to the probability of this point in the central area. So when we calculate, when we have one new example, x1 test, that is inside this area, this means that this probability is high, while if it's outside, then the probability is low. So if we have set up, for example, that our threshold equals 0.02, then in this case we have that the probability of xtext1 is higher than the threshold, so xtext1 is okay, while xtext2 is anomalous because its probability is less than threshold.
May I ask a question?
Yes, sure.
Is the added examples we are seeing now not added to the training set, but there's always, we have one new example
Exactly.
compared to the training set. It's not changing the training set.
Exactly, yeah. You have a training set made of, let's say, normal examples, and then you have a new one that you have to decide if it's normal or not.
Thank you.
Okay. So this is this is the algorithm. Then we see why it is important to evaluate an algorithm in order to check if it performs in a good way. In this case, we have to build an algorithm that is able to distinguish anomalies from normal examples. And in order to do so, we have to choose the fixtures, we have to tune the value of the threshold epsilon, etc. And how can we do this? And let's say that we have a set of non-anomalous data. For simplicity, let's say that y equals 0 is the label given to the non-anomalous example, and y equal 1 is the label given to anomalous example. So, as I was saying, we have some data that are non-anomalous, so their label is 0, and we have a training set of them. Okay, y equals 0 for all training example. Then we can think that we have another set that we call cross-validation set that is used to tune the values of the parameters of the algorithm. And then we have a test set that is used to evaluate the performance of the algorithm. And these two sets, the cross-validation and test set, they include a few anomalous examples that we have. So imagine that we have seen, okay, I have an example here. Imagine that the factory that builds these engines has seen 10,000 good engines in the past, from the beginning of the production. And in, I don't know, 10 years, just 20 of these engines were found to be anomalous, be broken. So we have, in this case, we have a data set in which we have 1,000 good engines and 20 bad engines. So we can think of using a training set made of 6,000 good engines and train the algorithm that we have seen on this, on this training set. Then we can also use a cross-validation set made of 2,000 good engines and 10 bad engines, and use this cross-validation set to tune the features that are to be used for finding the anomalies, and also the threshold that is used to calculate the probability. And then we can also think to have a test set made of 2,000 good engines and the other 10 bad engines. So what can we do? We can use this test set in order to evaluate the performance of the algorithm. So we train the algorithm on this training set. We fit the parameters of the distribution. Then we use this. Then we see how this algorithm performs on the cross-validation set, and we can try to change the value of epsilon or the features that we use in order to maximize the performance of the cross-validation set. And then once we have tuned these parameters, we can use the test in order to check if the algorithm is actually working well or not. An alternative that is used when there are very few anomalous examples is to use all of them in the cross-validation set in order to be able to tune better the epsilon and the features. But this can lead to overfitting. So this means that we can find an algorithm that works very well to the example which we have, but is not able to work well on new examples. So this is a problem that should be taken into consideration. In order to do the evaluation of the algorithm on the so what we do is to fit a model on the training set, on the cross-validation and the text set, predict the label of the new examples that are not included in the training set, and then calculate the performance. One metric that can be used is accuracy, so to calculate how many correct labels we have over all the labels. Or alternative metrics are, for example, precision, recall, true positive, false positive, or also F1 score. So these are other metrics that are used in machine learning. Okay, let me go to the end and let me try to compare anomaly detection and supervised learning.
Floriano,
yes,
you need to compute the threshold from the training and the test set, right? Or from the test set. So how are you computing the threshold? So what do? You try to minimize the error that you get?
you use the cross validation set in order to tune the threshold, so that the examples, the bad engines are correctly identified in some way.
So you want to minimize or to maximize the F1 score for the prediction that you get using the
Exactly. But this could lead to an overfitting of the model, because if you don't have a training set of really new examples, then you can have a model that perfectly fit the data you have, but is not able to work on new data.
Okay, I have maybe a scenario, really concrete, special scenario of monitoring of data centers, for example. So in a normal data center, behavior is this, that maybe in the week there is smaller traffic of CPU and memory and upload traffic. Then some peaks, there will be every time a user is starting some heavy action, some heavy process. Okay, this for me is not an anomaly, because this is very short. Then maybe in that weekend there will be all the backups. Okay, then the load is higher, the traffic is higher. This would be the normal case. So after 3 weeks, okay, maybe I have a forecast or examples for 3 weeks of this. My loads, data set, loads, traffic, memory, disk space, and all these things. And then after months, the backup doesn't run, and I don't have this traffic. So I don't have this data. Is this anomaly detection, or is this just machine learning? Could the anomaly detection algorithm find this, or?
Yes, because this situation in which you don't have the backup, this is the anomaly.
Yeah, in this case,
this is the anomaly. So you have a data set made of, for example, 6 months of system behavior, in which every Saturday there is this peak of activity because of the backup. Then in the 7th month, this backup doesn't happen for some problem of the system. This is the anomaly, and you will find that this example would have a very low probability, so this would go lower the threshold, and the system will raise the alarm. Oh, there is something that could be.
It's difficult to have this training set on data on each day. So how is the formula, or are there some frameworks to help me for this? Because I think it's just complicated to get the right algorithm for.
But in this case, it will mean that you put the weekday, right, as one of the features.
Yeah.
So the weekday will be a distinguishing feature, because when it's Saturday, the peak should be high, the value should be high. When it's not Saturday, it should be lower, right? So if you have a value where on Saturday the CPU load is low, this would be an anomaly. Right?
Yeah, no. Your question could be rephrased in how easy is to find the right features, and this is not easy at all.
Yeah.
So
I agree.
I think that the most difficult thing is identifying the feature, but also identifying the right metrics to evaluate the training and do the cross validation properly. Because if I am an engine producer, probably I would be sure that I identify all not working engine, even if I lose 10 engine more, instead of having one failed engine in the good one. So also identifying the right way to set up the threshold, it's not easy.
On the other end, an engine, the production of an engine costs a lot. So identifying an engine that is good as bad, this is
Yeah,
you will
but
lose a lot of
it's
money.
really
So it's
for Airbus, it's really higher. The problem if they put a failed engine on an airplane. So
I'm sure that it's much more important to be able to find all the bad engines. This is definitely true.
no, that's why it's difficult, because you have to
Yeah.
find the right balance. So it's not an easy task.
Yeah, that's true. Are there any other questions? So I just want to conclude briefly with some differences between anomaly detections and supervised learning. For example, the finding anomalous engine is a typical case of anomaly detection, because we have very few engines that are bad. While when we have a large number of positive and negative examples, then in this case it's easier and it's more effective to use some supervised learning algorithm able to classify, to distinguish positive from negative example and to do a classification of the example. Another difference is when you are not sure about the type of anomalies that could happen. In this case, you cannot have a labeling of all the different type of anomalies, because you don't know them. So in this case, using anomaly detection, you are able to find any type of anomalies independently of how many types you can have, while if you have enough positive examples, in any of the bad classes that you can have, then in this case used supervised learning is better. If you have the future positive example that are likely to be similar to the ones in the training set, which positive I mean the anomalies. So if the anomalies are, for example, in spam, there are different types of spam that are always them. So it's the typical, it's very, well, from time to time there is one spam email that comes to your inbox and they are able to, I mean, to not to be intercepted by the spam filter, but in general the type of spam are quite defined. So in this case you can use supervised learning. While, for example, when you talk about different type of fraudulent behavior on a website, this is much less defined. So in this case, anomaly detection could be preferable. And other types, I already said, when you want to find new and previously new defects that are not being seen before, then anomaly detection is better. If you have examples of defects that you already have found in the past and you just want to distinguish between them, then using supervised learning and classification is preferable. Monitoring machine in data centers is another type of anomaly detection, because that could be the case of the backup that doesn't work, but could be another cause of strange behavior. So this is a typical case of anomaly detection. weather prediction, if you have a predefined set of weather, sunny, raining, foggy, etc., then supervised learning could be better. Also, disease classification, if the set of diseases is finite, could be tackled with supervised learning, and so on and so forth. So it's this is the end of my presentation. Yeah, I hope that I have given to you an idea about anomaly detection, maybe not very deep because we didn't have much time. And then if you want to learn more about these topics, you can go to this course on Coursera, from which I have taken the examples here, and I want to thank the professor who have produced this course, because it's very interesting and useful. Thank you, and if there are any questions, I'm here.
Some question?
I can, yeah. Should I go? Set up. My question, I don't know if this works. Do you have at the Smart Data Factory projects where you are using this anonymous, so these algorithms, these methodologies on some use cases like exposed before, server monitoring, or other use cases? Can you name some?
Well, at the moment we don't have projects on that,
okay,
but we are open to new projects also on this field, because I think it's quite interesting for companies. So if you have some anomaly detection problem, please talk with us, and we can try to find out a solution.
Other question, and for instance, you are just developing some custom algorithms for every problem I have, or for example, because in the cloud, AWS, etc., there are just some frameworks that I can treat the data, I give the feature, and then he's returning me the outdated data, you know, the anomalies. Where do you making the difference from these frameworks that are just existing?
Well, I think that we are not proposing new algorithms for this type of activity, for anomaly detection. What we can provide is some expertise about how to be able to use already existing algorithms,
Okay.
because yeah, there are plenty of tools that you can use, but it's not always easy to find out how to use them.
But maybe it's more difficult to find the right feature, or to write the right data samples to use. Maybe
Yeah,
okay.
yeah.
Okay.
There was one more question, I think, here. No? No? Okay, answer. You?
Well, no, I just wanted to say that we already use, we have, as a company, we have, we already did something with the University of Bozen-Bolzano, with the economics department.
Okay.
Isolation forest we used. They used this option as for our problem.
Yeah, this is one typical algorithm that you use for anomaly detection.
Yeah.
What I have presented today is a very general idea, and these algorithms is very basic, but can be used in very many cases.
Then because we use time series in our software, and so we need something of this kind. And in the economic department, we were more adapted to search for help.
Okay.
Research. It's just an example.
Okay.
Thank you.
Thank you.
Maybe I have another question. I asked before if the data I am comparing is new, there's out on the market, or the training set should be self-evaluating. So, like, I have practical examples like we had the example before with user anomaly detection. So I have log on times, zone, and something, and usually the algorithms out on the market are like self-training. So with time, they're seeing if I'm shifting slowly, the behavior is not an anomaly, but if it detects a peaks, but maybe a user, now it's working on day and sleeping on night, but it's shifting or is traveling, so then the new training set should be another. So like is moving. When I use a training set now, tomorrow maybe it's deprecated. Yeah, the training set should be evolved, so it's difficult.
Yeah, this is the reason. This is the reason why, and in one of the slides, there was this sentence: please check if it is actually an anomaly or not, because and these activities, this check helps to find out if the training set you have used is still valid or need to be changed in order to capture other behaviors.
So you have to set up an anomaly detection on the anomaly detection.
Well, with a human being, it will always be
I was joking.
useful, let's say.
I was joking, but I am sure that someone is implementing a check, an automatic check on errors. If you find too many or too much errors, you have an alarm because maybe you have to retrain the system.
Yeah.
Could be.
I'm coming from the cyber security world, and there this is the normal that training sets have to change because it's never the same. It's always every day is a bit shifted or new cases. You have to exclude or include.